Let's take a look at what happens in a linear programming problem when we are faced with an unbounded region. For example, if we look at the feasible region described by this system of four inequalities, we end up with a shape like this. The four boundary lines here bound the left side and bottom, but not the right side, and not the top. This region goes on forever in those directions. And so it's what we call an unbounded region. There's no way to draw a circle that completely surrounds this region. Let's start by seeing what happens if we follow our normal procedure. So we could find all the corners of this region. They're labeled in this picture. And then we could plug those corners into the function we're hoping to minimize, their objective function, 3x plus 3y. And looking at the outputs at those three corners, we can identify the one that's least, and if we're trying to find the minimum value, that appears to be it. But the problem is, because the region's not bounded, we need to know how that affects the results. Notice that if I take a point up here with a large x and a large y, we'll end up with an output from our objective function that's also very big. We can make the output as big as we want by plugging in points that are far toward the upper right of the first quadrant. For example, if you plug in x equals 1 million and y equals 1 billion, you'll get an output that's very large. And so it becomes easy to see that there's no maximum value for this function. So the question is, did we really get a minimum value when we found the minimum at the three corners? Well, what we need to do to answer a question like this is to make the region bounded by drawing some extra edges. What we typically do is draw a couple artificial edges that are big enough that we chop off part of the region, but we don't chop off any of the corners that were already present. Now we end up adding some new corners when we draw these extra edges. And that's fine. All we're going to do is see if the new corners produce results that are bigger or smaller than the original corners from our unbounded region. So let's start by plugging in the corners. If we plug in 3, 0, which is one of our original corners, we get an output of 9. If we plug in 0, 4, which is one of our original corners, we get an output of 12. And if we plug in 1.5, comma 1, one of our original corners, we get an output of 7.5, just like from earlier. Now let's see what happens when we plug in the extra corners we got, the artificial corners, from adding these artificial edges to make the region bounded. So one of those corners is at 0, 6. That corner produces an output of 18. Another corner is at 6, 0, producing an output of 18. And another artificial corner is at 6, 6, producing an output of 36. So all of these three values were artificial corner values. Notice that they're all bigger than the values we got at the original corners. So what does that tell us? It tells us that the minimum value we found, 7.5, on the original corners, really was a true minimum. But if we'd been trying to find a maximum, we might have thought it was 12, but in fact that's not a maximum, because the artificial corners, at least one of them was able to produce a value that's even bigger. So because none of the artificial corners are smaller than the a true corner's value, we get a minimum. But because we get an artificial corner with an output that's bigger, we cannot say that the unbounded region has a maximum. There's no maximum when the artificial corner produces a bigger output, But there is a minimum when the artificial corners do not produce smaller outputs.